Good afternoon, students. Let us start the lab class. Today's experiment is Class B Push-Pull Amplifier. Let me read the brief theory. Class B amplifier is one of the power amplifier used for better amplification of the input wave. It gives a larger efficiency as compared to Class A power amplifier. In the theory class, you would have recalled whatever you have studied. Class A can have up to 50% of efficiency, whereas Class B can theoretically give up to 78.57% efficiency. So Class B amplifier with a single transistor can conduct only in one half cycle or 180 degree of the input waveform cycle. Two transistors of similar or complementary type can be used such that one of the transistor conducts in the positive half cycle and the other transistor conducts in the negative half cycle. So the output produced is traced in both cycles. Such a circuit is known as Class B push-pull amplifier. Or if it is biased, then it is also called as quasi-complementary push-pull transformerless power amplifier. Here, no need of using the transformer also. Hence, an output with low distortion is produced, which can be witnessed in the output waveforms. If it is Class B push-pull amplifier, we will have a distortion called crossover distortion. If it is quasi-complementary push-pull amplifier, transformerless, it is actually Class AB, which will have no such distortion. We are going to see both the circuits today. Now, this is the circuit diagram of Class B push-pull amplifier with crossover distortion. Yeah, you can see the circuit now. Okay, when the input signal is applied here, let me annotate. In the positive cycle, Q1 will conduct, and in the negative cycle, Q2 will conduct. You can see in the positive cycle, Q1's based emitter will have bias, and then you can see here, from this junction of the emitters, a load is connected and this portion is the ground. Now to Q1, a separate power supply is given. Let me change the color. This is in the positive half cycle. For Q1, whenever there is a input positive half cycle, then Q1 conducts, and from collector of Q1 to emitter of Q1 current flows, that flows through this load R1. Now in the negative cycle, Q2 conducts and the current flows in this direction from the lower power supply through R1 back to V3. So you can see in both the cycles, the conduction of current across R1 is in the opposite directions, corresponding to positive cycle and negative cycle. And we need two individual power supplies here. You can see V offset is 0, means DC voltage is 0, amplitude is 2 volts peak to peak, frequency is 50 Hertz. As this is a power amplifier, amplitude can be up to 2 volts or more also. And at the output you can see it is 30 volts DC, means correspond to a 2 volts input, we will get a 30 volts output. Now here the gain mainly depends on the supply voltage which we are giving. So we can say that there is 2 volts peak to peak is the input, and it is 30 volts on one peak, another 30 volts on the other peak, totally 60 volts peak to peak we can say with respect to ground. With respect to ground, it is 60 volts peak to peak, and input is 2 volts peak to peak. So 60 divided by 2 is 30 times is the voltage gain here along with the voltage gain, there is a current gain also here, because directly from supply voltage, current flows to the load R1. In our earlier cases, we always used to have one collector resistor. Here in this case, there is no resistor as such. That means both Q1 and Q2 are power transistors which must be able to handle current in amperes. So that way you can see after simulation, the simulator showing 30 volts at the top, minus 30 volts at the bottom with respect to ground. You can see, because the ground is the shorting off the negative of the upper battery and the positive of the lower battery, due to which with respect to ground, V2 is positive, whereas V3 is negative, because the negative terminal of V3 is connected to PNP transistor below. Now this is called push-pull configuration. Why the name push-pull? That name came because of the push-pull trains. In many hill stations, there is no space for the engine to take a U-turn also. So in such cases, for the same train, there used to be two engines. And those two engines, one was pushing from the back side, one was pulling from the front side. That was one reason. In many hilly areas, sometimes one engine is not sufficient as such. In general, train requires a plain land to move. Whereas if there are high slopes, then the train will not be able to move that way with lot of power. So more power is required. That is why two engines are there. One is called pulling engine at the front, and at the back side there is a pushing engine. So due to that concept, because of the train, the same term is used here also as push-pull amplifier. In this case, we can say in the positive cycle, NPN is pushing current down, and in the negative cycle, PNP is pulling current the other direction. We can say that way, because in PNP, current flows into the emitter, whereas in NPN, current flows out of the emitter. So you can say the upper one is the push transistor and lower one is the pull transistor. That's how this is called as a push-pull amplifier, and it is a class B amplifier because each transistor conducts for 180 only, for half cycle only. Now with this circuit, we have one particular problem called crossover distortion. Until the input reaches 0.7 volts, Q1 will not conduct, and until the input reaches minus 0.7 volts, Q2 will not conduct. So in between that 0.7 to minus 0.7, neither Q1 is on nor Q2 is on, and at that time there will be no current supply to the load. So I'll show you the waveform now. See, this is the waveform with crossover distortion. You can see here at this point and at this point. Again, you can see at this point and at this point. Everywhere you can see the crossover distortion. At some places it's slightly missing. That is because of the junction capacitances charging. The transistor, being a power transistor, will have slightly higher capacitance, due to which it is charging. Otherwise, you can see everywhere, here also, you can see a crossover distortion. Let me stop annotating and let me only underline. You can see here, 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 everywhere. Somewhere the simulator would have missed out that. Otherwise, you can see everywhere there is crossover distortion, means the both transistors are off in this region until, see, at this point, this particular point and this particular point. Now until input reaches 0.7 volts, NPN will not turn on. So this is turning on only when NPN is on. So let me change the color so as to indicate this is the place where NPN is on. And let me change the other color to indicate this is the place where PNP is on. So in between, until NPN is on, until PNP is on, in between there is no output across the resistor. That is at this place and this place. So that is called crossover distortion. Obviously, class B push-pull amplifier cannot be used for audio amplification, because in audio amplification part of the signal is lost. But we can say that class B is working within 180 degree or slightly less than 180 degree also, and the efficiency is higher. Now coming to the next circuit. If you have any questions in between, you can ask me. Otherwise, let me discuss the next circuit. This is the circuit without crossover distortion. Here you can see the input is given by means of these two capacitances. Here we need a capacitance. In the upper circuit, we don't have a capacitance, because the input signal is directly driving the base of the transistors, and there is no other DC power supply at the base. So AC can be directly given. But in the circuit below, we have this coupling capacitance or DC blocking capacitance. The reason is, you can see there is this R2 and R3 connected from the power supply. Slight biasing is given by means of this 47 kilo ohms resistance from V2 to Q1's base. Similarly, for Q2's base also, you can see this R3 is connected, 47K value is connected to the negative of V3. In this way, a slight biasing is given to the Q1 and Q2. So normally this Q1 and Q2 are slightly on. And when input signal is applied, they will turn on further. There is a mistake in this circuit diagram. The C1's end should be connected here. This should be connected here, and this is wrong. Okay, anyway, there is the mistake in the circuit diagram. When you simulate the circuit, you take care in this manner. C1 is connected directly to the base. C1 obviously cannot be connected to the supply voltage, right? So it is connected to the base. So in the positive cycle, when input signal is coming, Q1 will turn into saturation, and that is when further conduction will happen. Otherwise, slight DC current is already there at Q1, slight DC will be flowing there. Now in the negative cycle, Q2 will conduct, and this will happen this way. You can see in the negative cycle, the same signal is connected to the base of Q2 by means of this C2. In between them, you can see this 2.2K resistance. In between this and this. Now, if this 2.2K resistance is not there, then Q1 and Q2 will always be continuously on. So, this middle resistance R5 you use to prevent the continuous switching on and switching off of Q1 and Q2. So, in this case, the values are chosen in such a way that transistors are slightly above cutoff region. That is why you can see that 47K, 2.2K, 47K combination is there. The transistor will be slightly above cutoff region. That means the Q point is slightly above cutoff region. Later on, when we apply the input signal, in the positive cycle, Q1 will turn on. In the negative cycle, Q2 will turn on. In that way, this is a class AB operation. It is not exactly class B, but this is also push-pull only, because one is in the positive cycle, one is in the negative cycle. This is now class AB operation. So, I will show you the output waveform for this circuit. Now, this is the output waveform without crossover distortion, where you can see during the zero crossover, there is no distortion. You can see exactly in this line here, there is no crossover distortion anywhere. That is because the transistors are slightly on when the input signal is absent. Gradually they will turn on NPN will turn on one direction, PNP will turn on the other direction so that output is available. This is without crossover distortion. We can call it as class AB push-pull amplifier only. So these are the two circuits of today's experiment. One is with crossover distortion and the other one is without crossover distortion. Now procedure is, as you already know, apply a sine wave and you can increase the value of the load from 1K till 30K in steps. You can calculate the efficiency. Even the input can be increased. Input amplitude also can be increased from 2 volts to 30 volts. You have to note down the output voltage and output current by connecting the ammeter and the voltmeter there. In the simulator tool, here you can connect the ammeter and measure the current also. You can connect the voltmeter and measure the current also. Already this probe is there. That is to measure the voltage. So now, to calculate the efficiency, RL can be varied from 1 kilo ohms till 30 kilo ohms, and in each value of RL, for each value of RL, the load current and the load voltage can be measured and it can be tabulated. Now, as the load current and load voltage are AC in nature, its respective DC current can be found out as IL into 2 divided by pi. This formula you are already familiar. And then later on, DC power can be calculated as VCC into IDC. Now, AC power can be calculated by means of VL square divided by 2RL. Now, AC power is calculated and DC power is calculated. So, by means of this, we know the input power is DC, output power is AC. So, efficiency is output power divided by input power into 100. Now you can tabulate all the values and you can find out the efficiency in both the cases. In the case of class B with crossover distortion and with that class AB without crossover distortion. For both of the circuits, the efficiency can be measured. When once the efficiency is measured, then accordingly you can find out the optimum load. Why do we vary the load here? The reason is, wherever we get the maximum efficiency, that is going to be the optimum load. You already know about impedance matching. If the load is matched with the source impedance, then there will be maximum power transfer. So, in this type of amplifiers, we are not sure about the impedance as such, because impedance is dependent on those transistors only. There are very less external components here. You can see here, except for the transistors and the load, there are no other components at all. So how exactly do we find out the impedance? For which practically what we can do is, in this case, we can vary the load from 1 kilo ohms to 30 kilo ohms and we can find out at what particular value maximum impedance is occurring. Maximum efficiency is occurring, and that particular load is called as the optimum load for the given design of class B amplifier. It is the same case with class AB amplifier also. You can repeat the same experiment for that. Now with that, I have come to the end of today's experiment. If you have any questions, you can ask me. We are left with only one more experiment, that is class C tuned amplifier. We will be covering that in the next class. Okay, last week You could not submit the experiment because no assignment was created. Fine. I will be asking Prithviraj sir to create assignment for today's experiment. You can submit it. Prithviraj sir? Prithviraj sir, are you there? Okay, I will tell Prithviraj sir to create one assignment for today, and even the attendance link also he will post it in the Google class. If you have any other questions, you can ask me, or else I'll stop sharing the screen, and you can submit your observation books PDF in the Google class assignment. But meeting will be on. Those who have already installed PSpice into your laptop or desktop, if any of you have conducted the experiment, you can talk to me now. If at all any of you have already started working on these experiments, has anybody done that? If anybody has tried out, you can let me know. Okay, as there is no response, I will stop sharing the screen now, and meeting will be on. You can submit your observation book.